So if we can put ourselves in the mindset of people going back, 500 years ago, there is no science. Science doesn't exist. And, things like TV and radio don't exist, and the vast majority of people are illiterate. I mean, literacy is probably in Europe at that point around 1% of the population. And the one thing everybody had was dark skies. There was very little pollution, and there was no street lighting, and everyone could look up and they could see the stars. And the first thing you'll note when you're in Big Bear, right? I mean, you're almost in that environment. You can all look up and you can see the gorgeous night sky. And the first thing you notice is that the stars positions relative to each other, and they form the constellations and so on. One slide, yes. So this was entertainment for people back in the day. They could look up at the stars and they formed these beautiful fixed patterns, and of course people had to wonder what these things were and what our relationship to them was. But in addition, of course, to the fixed pattern of stars, there were these planets, and at this point the Earth was not recognized as being a planet. The Earth was the center of the universe, and were these objects that moved relative to the stars. So that the original Greek word for planet means wanderer. They're wandering relative to the star. And the cosmology of the day states that the Earth is the center of the universe, and that everything orbits around the Earth. Everything rotates around the Earth. And when you look at the stars, that's quite sensible. The stars appear, they rise in the east, they set in the west, and as you go throughout the various seasons, you see different star patterns, but they all hold fixed patterns, and they repeat here. And so the model that the Earth is the center of the universe and that everything goes around the Earth makes good sense with respect to the stars. But there's a problem with the planets. So if we can go to the next slide. The problem with the planets is retrograde motion. When you observe a planet moving relative to the stars, every once in a while that planet appears to go backwards and then forward again. So that's called retrograde motion. And the problem is, if everything is simply traveling around the Earth, there should be no retrograde motion. Everything should just go on a nice circular path around the Earth. So in order to keep with this model of everything going around the Earth, they introduced, going back thousands of years now, this idea of retrograde motion. So if we can go to the next slide. In retrograde motion, the planet actually doesn't go directly around the Earth. You see that white dot that's going directly around the Earth. The planet then goes in a circular orbit around this spot. And so, as you can see from the point of view of an observer on Earth, the planet will occasionally appear to go backwards. So that's great. That's a first-order explanation for this retrograde motion, and it maintains perfect circles and everything going around the Earth. The problem is, when you precisely measure the positions of planets, especially Mars, you cannot make this model work. It deviates, the position of Mars deviates from the simple model. So what they did at that point was that red dot that represents the planet, they made that yet another retrograde spot, and then they would have the planet do another circle. So you had a circle within a circle. So you had two levels of retrograde. And then that still didn't work, and they kept adding more and more of these circles. They're called epicycles, and the planet would go in a circle around an epicycle, which would go in a circle around an epicycle, which would go in a circle around an epicycle, which would go in a circle around an epicycle. And when the whole system finally collapsed, they had, for the case of Mars, 56 epicycles. So calculating the positions of planets was incredibly difficult, and given enough time, the model would never ever match the observations. So in 1530, the thing that becomes the precursor to modern science was introduced, the idea that the Earth and all the other planets go around the sun. So if we can see the next slide. This was introduced by the famous Polish mathematician and astronomer Copernicus, and he was aware of the fact that this idea that the Earth is a planet and that it orbits the sun and all the other planets orbit the sun was such a revolutionary and radical idea that bad things could happen to him. And he withheld publication until he was on his deathbed. So this is in 1530, almost 500 years ago. The nifty thing about this theory is it provides a much simpler explanation for retrograde motion. So if we go to the next slide. This will take a second to load, but in this slide, all the planets are going around the sun, and what happens is, because the Earth is closer to the sun, it goes faster than Mars, and as it catches up to Mars and goes past it, simply from the point of view of the observer on Earth, Mars appears to go backwards. So there you have a nice simple explanation, and it doesn't require epicycles, and everything is in a nice circular motion. The really radical idea here is that the Earth is a planet, and you might say that the Earth was the first planet ever discovered. It was discovered roughly in 1530. All the other planets, of course, were known in antiquity. You could see them with your eye. So this is this provides a much simpler way now to calculate the motions of planets, but the problem is it's still not great. It's still, if you follow the orbit of Mars carefully, this model still does not give you a beautiful representation of the orbit of Mars. And the problem at this point is that Copernicus keeps perfectly circular motion. At this point, everybody knows everything in the heavens is perfect, and the only perfect motion is a circular motion, and as long as you're stuck in circular motions, you still cannot make the model fit the observations. So we're still in pre-science, but we're now approaching science. So if we go to the next slide. Yeah, so along comes this crazy Italian monk, Giordano Bruno, and he publishes this book in 1584. Relatively few people were intellectuals who could read, had read Copernicus, and Bruno fully buys into Copernicus's idea, and then he goes further. Because at this point, the stars were not considered like the sun. They were dots of light in the sky. But Copernicus posits that the sun is a star, and that all the other stars have planets, and that life on these other planets is probably common. So, today you would yawn if you hear that. That's the premise for every episode of Star Trek and Star Wars. But at that time, this was such a revolutionary idea that Bruno was condemned as a heretic by the Catholic Church, and in 1600, a fairly nasty thing happened. If you hit the forward button on the slide, things did not in the end work out so well for Bruno. He was burned at the stake at a public plaza in Rome, and there's a big statue to Bruno there today if you go there. So you might say back then, 416 years ago, that this field was really hot. All right. Bad pun, but I like. What can you say? Okay, so if we can go, so we're still in pre-science, and so if we can go on to the next slide. Science, what I identify as science, is basically invented by Kepler between the years 1609 and 1619. Tycho, the great Danish astronomer, and the last naked-eye astronomer and the greatest naked-eye astronomer of all time, felt that the only way the problem of the planetary motions could be solved was to make super precise measurements. So he spends from the 1580s until his death in the early 1600s very precisely measuring the position of Mars relative to the stars, and he invents a number of instruments to do this more precisely than anybody else. And the enormous innovation that Tycho had was not only did he measure the position, but he very carefully estimated his observational error. For instance, you can make repeated measurements and note that there are very slight differences in them, and presumably that's due to a measurement error. And using these techniques, he would actually estimate his measurement error. So he had something like 20 or 30 years of very precise measurements of Mars, and he had measurement errors associated with each measurement. And this is now, now we're tiptoeing on science. What separates science from religion or any of the belief system is that you make measurements, but you also acknowledge that there are errors, and you have to estimate the errors. So after a long and difficult study, a struggle after Tycho dies, Kepler finally gets all of the measurements, and he sits down, and he's easily the smartest mathematician in the world at the time. He's probably the smartest mathematician who'd ever lived up until that time, and would remain so until Newton came along a couple of generations later. And he very carefully works out the measurements of Mars, and he does just remarkable. For instance, in about 1607, he had come up with a model for the motion of Earth and Mars that would very precisely, more precisely than anything ever came before, mark out the orbit of Mars. But he noted that the model did not quite fit the data to within the measurement error, and he was well aware that the measurement errors were excellent estimates, and having produced the best model ever in the history of the world, he balled it up into all his paper and threw it in the garbage. And that's remarkable, and maybe that's the beginning of science. But in 1609, he makes the first of three incredible breakthroughs, and the first breakthrough really was an intellectual leap forward. So if we go to the next slide, what he does in the first law of planetary motion is he gets rid of the circle. He says planets do not travel in circles. They can travel in circles. A circle is a special case, but in general they travel in elliptical orbits. So the circle can get stretched out. And with that, he could now trace out the orbit of Mars to within Tycho's measurement errors perfectly. And this is maybe even more radical than the idea that the Earth goes around the sun, because he got rid of the circle, and just remarkable. And then over the next 10 years, he comes up with the next two laws of planetary motion and built the first complete working model for the solar system. And in fact, it was with this knowledge that Newton was able to then go on and come up with the law of universal gravity, because he knew that whatever form he chose had to collapse down to Kepler's laws of motion, because Kepler's laws of motion are right. And in fact, today, when we fit planetary orbits, we use Kepler's laws. For the most part, we don't go to the more complicated Newtonian solution, because Kepler's laws are right. They're correct. So just a remarkable thing. And one of the remarkable things is, in the middle of this struggle, sometime around 1615, almost exactly 400 years ago, 2 years out from this work, to defend his mother from a charge of witchcraft. So just a remarkable achievement, and it's just incredibly hard to even put ourselves in the mindset of the people back then. So we can go on to the next slide. Okay, so you see that the motions of the planets and the idea that the sun is a star and that other stars have planets predate science, and were one of the major, if not the major, motivations for the invention of modern science. And what I mean by modern science is that you combine precise measurements, measurement uncertainties, and mathematical models, and you insist that the mathematical model fit the observation to within the measurement uncertainties. So, this is almost exactly the time the telescope gets invented. It's invented sometime between 1608 and 1609, and people immediately thought, well, let's look for planets around other stars. And the obvious thing is you point your telescope to the star, and you try to find the teeny faint planet right next to it. And of course, it's technically impossible with that technology, because even a giant planet like Jupiter is 1 billion times fainter than the sun, and it's right next to the sun. So it's like trying to find a firefly that's sitting right next to a thermonuclear bomb going off. You just can't see it in the glare of the bomb. So the main way that people have been searching for planets around other stars for the last 100 years is to look for the gravitational influence the planet has on the stars. So if we can play this little video. As the planet orbits the star, it kicks the star into a small counter-orbit. This is just Newton's third law. For every action, there's an equal and opposite reaction. So in the case of the solar system, to first you can consisting of the sun, Jupiter, everything else in the solar system is less than half as massive as Jupiter. And as Jupiter makes a 12-year orbit around the sun, it kicks the sun into a counter-orbit that's also 12 years. And because the sun is 1,000 times more massive than Jupiter, the center of mass lies just outside of the sun's surface, and the sun makes this 12-year orbit around a point just outside of its surface. And this has been the idea for the last 100 years. And the first way that people attempted to do this is called astrometry, where you simply look at nearby stars and you try to measure their position relative to more distant stars and try to see the nearby star wobble about relative to the more distant stars. And Peter Van de Kamp famously did this for most of his career, and in the 1960s even announced that Barnard's star had a planet based on. And reanalysis and subsequent observations have ruled this out. But Van de Kamp was really ahead of the field because he felt that most stars had planets and that we had to go out there and try to observe them. So the second way to find a planet also relies on the same idea that the planet kicks the star into a counter-orbit, and that's called Doppler velocity. So if we go to the next slide. So here again, the same idea. The unseen planet orbits the star. It kicks the star into a small counter-orbit. For half of the orbit, the star is approaching an observer on Earth, and the light from by the Doppler shift, so it gets compressed to slightly shorter wavelengths. Astronomers call that a blue shift because blue is the shortest wavelength that humans can see. For the other half of the orbit, the star is receding from the observer on Earth, and the light from the star gets stretched out to slightly longer wavelengths. Astronomers call that a red shift because red is the longest wavelength that humans can see. And so if you can measure the Doppler shift of the star getting smaller and larger, you can actually work out the velocity of the star. And if you see it periodically moving towards us and away from us, you will have detected the planet. And in fact, you can work out the mass of the planet and the orbit of the planet. So, you know, for some of you, the Doppler shift may seem a little esoteric, but in fact, it's used. So in the next slide, you can see one example of the Doppler shift being used. Oh, okay. Well, we'll get to that in a minute. Yeah, go ahead to that next slide. So here we go. So the instrumental heart of all of the Doppler shift techniques is a high-resolution shell spectrograph. So at the top upper left of the figure here, you see the entrance slit to a spectrometer. So for people doing spectroscopy, the telescope is just a light bucket. It just gathers light, and it brings the light to a focus at the entrance slit of a spectrometer, and then once the light goes through that entrance slit, the light then begins diverging, and you can see that purple line coming down indicating the direction of the light, and the light is diverging until at the lower right it hits the so-called collimating mirror, and this is a mirror with a parabola ground into it, and it converts that diverging beam of light into a parallel beam of light and sends it off to the shell grating, which is on the left middle of this figure. And the shell grating is just basically, it's like a prism. The main thing it does is it separates the light into its component colors. The light then comes through two prisms that separate the various orders of the shell and sends the light on into a very fast camera. And at the back of the camera, there's a CCD, which is the same sort of detector that you have in your fancy iPhones. So we can go on to the next slide. This shows what an actual shell image looks like. You can see each one of these stripes of light. Each one of these stripes of light is typically about 50 angstroms. The human eye can see from about 4,000 angstroms in the blue to about 7,000 angstroms in the red, and each one of these stripes is about 50 angstroms. And the enormous thing that these shell spectrometers do is they allow astronomers to get a spectrum of the star that is extremely high resolution and covers the entire wavelength scale of the star in the visible. So prior to shell spectrometers, astronomers could either get full wavelength coverage but only at very low resolution, or they could get very high resolution but only over a couple of angstroms. So shells allow you to do both things, and the fact is that this work only is able to exist because of shell spectrometers, which are themselves based on the invention of CCDs, the invention of advanced ray tracing software, and fancy high-speed computing and disk storage. So we sit on top of all of these discoveries. And you'll see in the spectrum, for instance, if you look in the middle of the yellow, there are these two broad dark lines. Yeah, that's exactly those. That's the famous sodium D lines, the famous sodium doublet. Most of those lines are due to iron and nickel, but they're also due to calcium and every other element. You can actually, from the spectrum, you can actually figure out chemically what the star is made of, which is a pretty wild thing. You can, for a star that's hundreds of light years away, and you can actually figure out exactly what it's composed of. So that's pretty remarkable. From this, you can also figure out the surface temperature of the star. You can figure out the surface pressure of the star. You can figure out the rotational velocity, the spin velocity of the star. So that's all nifty and cool. And the fact is, we don't care about any of that. All we care about is the Doppler shift. And what that means is, if a star is moving towards us, those individual lines will move. Okay, good. So this is part of the danger of giving a talk from the other side of the world. So thanks for hanging in there with me. Okay, so what I'm going to do is I'm going to pull up the talk here so that I'll know what slide that hopefully we're on, and hopefully this will only take a second. Open recent. All right, there we go. Oh, I've got your video. Okay, so I don't need to do that. Okay. Okay, good. Okay, so we'll go on to the next slide. I love to put pictures of my collaborators here. This is Steve Vogt at UC Santa Cruz. He's the guy who designed and built the world's first modern shell spectrometer, the Hamilton spectrometer that we saw earlier. And I love this image of him because he looks like an optical wizard. And in fact, he built the spectrometer at Keck, the high res. He's built the new APF spectrometer that we're using. And honestly, I can say that I wouldn't have had a career if it wasn't for Steve Vogt, and he continues to be one of my absolute closest collaborators. So we'll go on to the next slide. So again, the Doppler shift may seem a little esoteric, but it's used every day in real life. Here you see the classic thing of the highway patrol with their radar guns. The radar gun simply shoots out a radio wave of known wavelength, and if you're in a car approaching the officer, the radio wave will bounce off your car. Because you're approaching the officer, it'll be bounced back at a shorter wavelength. It gets compressed as it bounces off your car, and the amount by which it shifts to shorter wavelength tells officer how fast you're going, and if you're over the limit, we all know what happens. So you can see from this example, if we go on to the next slide, that the Doppler effect can be used for both good or evil. Okay, so we go on to the next slide. So what would our own solar system look like? Imagine that we're aliens orbiting some other star, and we use this technique to look at the solar system. This would actually show what it looks like. You see the sinusoidal pattern, this S-shaped pattern that repeats every 12 years. So you can go ahead and click the slide one more time. And this 12-year pattern is Jupiter. So you can directly see Jupiter in this diagram. And then the second thing you can click it one more time, you can see this thing goes up and down by about 10 meters a second. So knowing the period and the amplitude, you can actually work out the mass of Jupiter. And the fact that this curve is so smooth, so sinusoidal, tells you to first order the orbit of Jupiter is very close to being a circle. It turns out it's just only 6% out from being a perfect circle. You'll notice something else. There is a high peak followed by a low peak followed by a high peak. The peak of the curve is going up and down. That's due to Saturn. So Saturn is the next most massive planet. Jupiter's about 300 Earth masses and Saturn's about 100 Earth masses. Saturn has a period of 29 years and it causes the sun to wobble by about 3 meters a second. So with current technology, these are the two planets in the solar system we can detect. So we'll go on to the next slide. So this is all great, but prior to 1995, there were no known planets. It's remarkable to think that going back just one generation, just 20 some odd years ago, there were no known extrasolar planets. We'd had Star Trek and Star Wars for decades at that point, but we had no known star that we could point to and say it has planets. And in October of 1995, Michel Mayor and Didier Queloz made this remarkable discovery announcement that the bright nearby star 51 Peg has this planet, and you can see from this diagram it's going back and forth every 4 days. Well, we have nothing like that in the solar system, and nobody had ever dreamed that something like this could exist. And it's going up and down by about 50 meters a second, so you can work out that the mass of this thing is about a half of Jupiter. It's a giant planet like Jupiter and Saturn. And nobody had ever dreamed these things could exist. So when it was first announced in early October of 95, it actually got very little publicity. First of all, over the preceding 50 years, the first planet ever had been announced a number of times, and the one thing they all had in common was that they were horribly wrong. And secondly, this never been suggested. Prior to this point, all theories of planet formation posited that planetary systems would all look like our own, with small rocky planets in close, giant planets like Jupiter and Saturn further out, all orbiting in beautifully nested concentric circular orbits like we see in our own solar system. So this thing was a shock, and people thought it must be nutty, it must be wrong. So it turned out that Jeff Marcy and I had 4 nights at Lick Observatory about a week after this was announced, and that first sinusoid that you see there represents those 4 nights. And our problem, we had been taking data since 1998, our problem was computational speed. An object at the telescope would take 5 minutes to take the observation, but the analysis of that observation would take 6 hours on the computer. And for that reason, we literally could not reduce our own data. We had to use all of our precious computer cycles to develop the software to extract the signal. But in this case, we had only a single star, and it was all we cared about, and so we put all of our computer power for that first 4 nights into reducing this, and lo and behold, we got exactly the result that Michel Mayor and Didier Queloz had stated, and we were blown away. And we put this on at that time, the brand new World Wide Web. And this image traveled around the world within about a day. And about 3 days later, our phone began ringing off the hook, and it didn't stop ringing for about a year. New York Times, Washington Post, everybody in the world called. It was really bizarre. For me, it was personally a very bizarre time because up until that time, nobody knew we existed. I was like a guy in a basement bunker. People would slide Cheetos and Diet Coke under the door, and I would just be working on software analysis. And suddenly, we're on Nightline with Ted Koppel, and we're on the front page of all the papers. So it was very, very odd. And it was also a pain in the ass because we had all this data that we needed to reduce. So in that figure, you'll see after the first 4 days, we, of course, continue to observe it very heavily, and that's the first 1 month of data. And you can see this thing goes up and down in a perfect sinusoid like a metronome. And, here we are 20 some odd years later, and that's still the case. This thing just goes back and forth like a perfect metronome. It never changes. So these things are now called hot Jupiters, and if you see in the next slide, why that is. One of the nifty things about these hot Jupiters is you can actually build a little model on a piece of paper in which everything is exactly to scale. So 51 Peg is a sun-like star. It's similar to the radius of the sun. Jupiter-like planets are about 1/10 the radius of the sun, and in this case, it orbits at about 11 stellar radii from the star. So it's incredibly hot, as you can see there. It's like of order 1,500, 2,000 K. So these things are now called hot Jupiters. And when they were first discovered, people were worried that the planet would boil away. But it turns out Jupiter-mass planets have a lot of gravity. And over the lifetime of the main sequence of the star, the planet loses 1% of its mass. And these things are, at that time, people thought this was incredibly rare, that, we found this because they're the easiest things to find. They only take 4 days to orbit. They have a huge signal, but they must be very rare. We now know they're very common. About 1% of stars have these hot Jupiters. So we can go on to the next slide. So this is late October of 95. And once again, this field of extrasolar planets is incredibly hot, although fortunately for us, nobody is proposing. But one of the great things that happened, research groups at Berkeley who had just taken new computers in for projects that they weren't going to use them for another 6 months or a year, turned to us and said, "Do you want to use our computers?" And we put together an armada of about 20 computers between October. Okay, is that working better? Okay. Okay, so basically from late October of 96, I hardly ever left my office. I was sitting there at the controls of about 20 computers, reducing our 9-year backlog of stars. Any given star to reduce all the observations would take anywhere from half a day to several weeks, and I would continuously monitor these 20 computers. Whenever a job finished, I would load the next job and then look at the results. And by December, we were starting to get some really interesting looking results, including, and by early January, we confirmed that we had our next 2 planets, and these things ended up in early February on the cover of Time magazine. But this is another very early planet that came out of this. This is 16 Cygni b. So this is, of the 9,000 stars in the Bright Star catalog, this is the star most like the sun. If you were to overlay the spectrum of the star on top of the sun, you wouldn't be able to tell the difference. And as you can see, like the sun, it has a planet. In this case, the orbital period is about 2 years, and the mass is about 2 Jupiter masses, so that seems all pretty good. But you notice the shape of this orbit is no longer that smooth S shape, that smooth sinusoid. This now looks like a sawtooth. This is telling us that the orbit is not circular. The orbit is extremely eccentric. So if you go to the next slide, or the next, hit the next button, yeah, so here is an overlay of what that orbit looks like when placed on top of the solar system. You can see how wildly eccentric it is. It actually, at closest approach to its star, enters inside the orbit of Venus, and at furthest approach goes well up beyond the orbit of Mars. So if we had such a planet in the solar system, we wouldn't be here. It would act like a giant gravitational bowling ball, and it would have scattered all of the little planets in the inner part of the solar system out, and there would be no habitable orbit left that would be stable in the system. So these eccentric planets initially were thought to be very rare because people still had this mindset based on the model of the solar system that all planets would be in circular orbits, and we now know these eccentric orbits are extremely common, and they're probably not good places to look for life. So if we can go on to the next slide. So there are early lessons. Like I said, prior to the discovery of planets, everybody knew all planetary systems would look like our own. And by everybody, I don't just mean the science fiction producers and writers, but every astrophysicist going back 200 years had been building models of planetary formation that always ended up with small rocky planets in close and giant planets further out. And so the first lesson, you can hit the next button on the slide. The first lesson is that humans aren't really very bright. We're not very imaginative. When you are trying to extrapolate based on a sample of 1, you're actually often worse off than trying to extrapolate from a sample of 0, because you have blinders on and you can't even imagine any other possibility. And this is a lesson that I learned from this and that I carry to me with it to this day. So if we can go on to the next slide. Yeah, so back in the early days, you find a couple of massive planets that are now relatively easy to find, and you make the cover of Time magazine. Things are much tougher now. So we go on to, one of the interesting things, of course, about this is you notice that this also was at a time when an election involved a Clinton, so things seem to stay the same. We can go on to the next slide. What we've learned, you find big planets, that's kind of fun, but it quickly becomes kind of boring, and we want to find small Earth-like planets. I mean, we want to know, is there anybody else out there? Is there life out there? And what we've since learned is that nature is very cruel and doesn't give up secrets easily, and that most of the interesting planets, the small planets, they come in packed systems, often with 3, 4, 5, 6 planets tightly close into the star, and therefore you have planet-planet interactions, and you need hundreds of observations, so you need to take a hell of a lot more data to disentangle these complicated signals. So the rest of this talk will go more into the more interesting planets that we've been finding more recently. So we can go on to the next slide. This is one of the first of these new types of planets. This is data that I took here at the Anglo-Australian telescope back in 2007. We had been making the argument for a while that we needed to have a high cadence observation. Typically, up until that point, we would get 4 or 5 nights on the telescope, and then we would come back 3 or 4 months later, and you might end up with 5 observations. And we knew the star was varying, but we couldn't figure out what was going on. And finally, in 2007, they gave us 48 straight nights at the telescope. And we observed the star every single night. And we were immediately able to disentangle the wild, crazy stuff that was going on here. You can see a repeating pattern every 4 days that has an amplitude of only about 3 meters a second. It was the very first super-Earth ever discovered. This is about a 5 Earth mass planet in a 4-day orbit. Again, super-Earths were unthought of. Everybody thought Earth was about the largest you'd get for terrestrial planets, and then you took a step up to Neptune mass planets, which is about 15 Earth masses. And this was a new class of planets that emerged. And then you see on top of it, there's this longer period with about 1 month. That's a Neptune mass planet in a 1-month orbit. And it turns out when you have even more data, we can go on to the next slide, that there's a third planet in this system in a 90-day orbit, and that planet is slightly eccentric, and it's about 2 Neptune masses. So this was an early harbinger of the fact that there was this new class of planets called super-Earths, and that you would often get these tightly packed systems of planets, which some amount of data, and for which you need high cadence to disentangle the signals. To the next slide. So again, these observations were made at the Anglo-Australian telescope. I came when I was a staff astronomer here, and I came here specifically to get access to this telescope, because at that time this was the biggest telescope in the southern hemisphere, and they had an shell spectrometer. And I brought an iodine cell, And I stayed here long enough to get long-term status on the telescope, and as you can see, to this day, in telescope. Okay. All right, so can you see me? Okay, I'm getting a thing going. Okay, good. Okay, great. So one of the challenges of observing at the Anglo-Australian telescope, if we go on to the next slide, is that the whole mountaintop is covered with these giant-tailed rats. They're everywhere. Often at midnight, I would walk from the dome to the lodge, and this is the path to the lodge. To get something to drink, to get a sandwich or something, and these things are all over the path, and they won't move. I've learned to hate these things, and everybody who lives in the Australian countryside hates kangaroos because everybody has wrecked a car by hitting them. They're just incredibly annoying. And extraordinarily stupid beasts. So everywhere you go, you got problems. Here, the problems are the damn kangaroos. So we go on to the next slide. So here's another one of these extraordinarily packed systems. In this case, from the HARPS, which again is production of Michel Mayor and Didier Queloz, and the red data is from our Keck project with Steve Vogt. And each of these two telescopes, in this case, have produced about 125 observations. So this is actually 250 observations, and as you can see, there is 6 different signals in here, 6 or 7, I can't even count anymore. And you need this many observations to disentangle what's going on. So you see there's a relatively large amplitude sinusoid in a 3-day period, and then a 5.7-day period, and a 12-day period, and a 37-day period, and so on. So it turns out this star is an M dwarf, one of these red dwarf stars. It's about half the mass of the sun. It turns out when a star is about half the mass of the sun, it's only emitting about 1% the light the sun is emitting. So the so-called habitable zone around these stars is much closer to the star. And when astronomers refer to the habitable zone, all they mean is that this planet is the right distance from the star to potentially have liquid water. That's all it means. But in this case, that 37-day planet is notable because that's in the habitable zone of the star, and it's about 3 Earth masses. So this is a super Earth in the habitable zone. Because it's 3 Earth masses, it's presumably made out of rock. It might have water. This is one of the very first potentially habitable planets to emerge. So if we can go on to the next slide. Yeah, so this shows the habitable zone. On the x-axis, you have the distance from the star, and this is a logarithmic scale, 1/10 of the Earth-Sun distance, 1 Earth-Sun distance, 10 Earth-Sun distances. And you can see the sun and the solar system at the top. And then Gliese 581, this red dwarf, below it, and because it's a red dwarf, it puts out much less energy than the sun. And the habitable zone, that blue stripe of light, is much closer to the star. So if you hit the next button on the slide, you can see that 37-day planet is right smack in the middle of the potentially habitable zone. So if we can go on to the next slide. So one of the other main platforms that we've been using over the last 20 years is the Keck telescope on the hopefully extinct volcano of Mauna Kea. And this is, at this moment at least, still the world's largest telescope. And the spectrometer was built by Steve Vogt, who built the first shell ever at Lick. We're going to the next slide. We see our newest platform, which is the Magellan telescope. These are two 6.5 meter telescopes that sit side by side at Las Campanas in Chile, and Las Campanas is the observatory that is owned and run by the institution. And the Magellan telescopes are 50% owned by Carnegie, and then they're also a partnership with Harvard, MIT, Arizona, and Michigan. And the one on the left is where we have the new planet hunting spectrometer. So prior to the planet hunting spectrometer, the planet finding spectrometer, all the spectrometers we had used at Lick, in Australia, at Keck, they were general purpose shell spectrometers. They were designed for astronomers to study everything from nearby to go to different wavelength regions. They weren't stabilized. And we realized to get to higher precision, we needed to build a purpose-built spectrometer. So it looks like we've just lost the video again, but it's hopefully, there we go, it's come back. So this was our first purpose-built spectrometer. And the next slide. This shows the spectrometer. So the prior spectrometers we had used were huge. They were the size of a living room with giant steel I-beams sunk in concrete and optics hung off of these steel I-beams. And they were so large you couldn't temperature control them. So the temperature variations would cause the metals to expand and contract. It would cause the optics to expand and contract. So they weren't stabilized in any sense. They could be moved, and they would jitter on all time scales. Because the problem is that the effect we're looking for is very teeny. At 3 meters a second, that corresponds to about 1/1000th the width of a pixel. So that's about 60 or 70 silicon atoms on the CCD substrate, and everything's wiggling about at that level. It's very difficult. So this was a new design that was originally dreamed up by Steve Scheckman, another extraordinarily close collaborator. And this is a so-called R4 design. The light actually makes a double pass through the spectrograph. It goes through all the optics twice, and that allows you to build a much smaller spectrometer. So this thing is now, the footprint of this thing is about the size of a ping pong table. So now you can temperature control it. So the front wall is off, so you can see the internal optics. On the far right is the shell grating in that black can, and on the far left in that silver can is the CCD, and all the optics are in between. And you can see all around it is 4-inch thick styrofoam. So this thing is massively insulated, and when it's in use, there's a big styrofoam cover on the front end. And then we internally heat the entire thing to 27 degrees centigrade. Because at Las Campanas, you're at 8,000 feet, and even though you're in the Atacama Desert, at 8,000 feet, it never gets to 27 degrees. So you heat it to 27 degrees, and we hold it fixed at that temperature to plus or minus 1/100th of a degree. And that temperature is maintained all the time, all year round. And nothing is allowed to move. There's no way to move the optics. There's no way to change everything. Everything is fixed. So you have mechanical stability, and you have temperature stability. And this is the first spectrometer that I've ever used where you come back a month or two later, and the focus has not changed. The focus never changes here, and that's so. If we go on to the next slide, sure. No, it's double fast increase. The grating is at one far end, so it's only hit once. The light goes the light starts off on the far left. It goes through all the optics. It hits the grating on the far right. Then it goes through all of the optics again, and then it goes into the CCD. So it only hits the grating and the CCD once. They're at the two extreme positions, and it's everything else that the light goes through twice. Yes. No, I haven't gone into the technical details, but we have an iodine absorption cell. That's what you personally calibrated back in 1992, and that was the breakthrough that allowed us to get to this level of precision. And so we have the starlight goes through an iodine absorption cell. It picks up the absorption of iodine, so we have all these iodine lines, and we look for the stellar lines to move relative to the iodine lines. And it was your spectrum at the Fourier transform spectrometer that was the initial key to the breakthrough. We spent 8 years writing this software, and we were 5 years into the project when we finally got that FTS spectrum from you, and that was the critical breakthrough in this project. So it's one of the reasons this is a great privilege for me to be able to give this talk today. Not at all. So we can go on to the next slide. So this is on the right is Steve Scheckman. He's the guy who did the design for PFS. And on the left is Jeff Crane. Jeff is the guy who actually did the subsequent detailed design and actually physically built PFS. And this is in the Carnegie Optical Shop in Pasadena. This is in October or November of 2009, just before we shipped the spectrometer. And I desperately wanted to get some spectra from this newest shell so I could begin working on the software. So you see there, Scheck is sitting down with a mirror in his hand, and he's reflecting sunlight from the window into the spectrometer so that I could get a spectrum to begin working with. And the reason I like this is because when you become a guru at the level of Scheck, you actually can become one with the instrument. So if we can go on to the next slide. So this is also at Las Campanas. You can see it's the high desert, 8,000 feet, in the southern Atacama Desert. And it's a lot like the American Southwest. There's little scrubby plants and cactus, and there's lizards and birds of prey, and there's also, it's kind of weird, there's llamas who wander around, and there's donkeys that wander around, and you have to drive a little bit carefully because they don't always get off of the road. And I like this picture because it's got the skull there, and of course it's an old saying in science, publish or perish. So maybe this guy didn't publish enough. So we can go on to the next slide. So this is the huge advantage of these purpose-built spectrometers. The first purpose-built spectrometer to do precision velocities was HARPS, the project with Michel Mayor and Didier Queloz, and the second one was PFS. So in this case, this is another one of these M dwarfs, these faint red dwarfs, and the green observations are from the Anglo-Australian telescope. And with these green observations in 2009, we discovered this long period planet. This is a Jupiter mass planet that takes about 9 years to orbit the star, and it was the first giant planet found around an M dwarf, so it was kind of nifty. But you can see how crappy the observations are. With HARPS is the red data, and the blue data is PFS, and you can see how beautifully they fit on the data, how dramatically superior they are, because the spectrometer is built specifically for this purpose. And signal, but also look for residuals. And so if you go on Keplerian or second Keplerian. Okay. Okay. So, okay, we're back. Good. Yeah. So, are you able to go to the next slide? There we go. Yeah. Yep. So, in the next slide, you see that there's these teeny residuals that now go up and down by only about 1 or 2 meters a second. HARPS and PFS data, and this has a period of about 33 days, and it's about 2 Earth masses. So again, this is a super Earth that's in a potentially habitable zone around one of these teeny red dwarfs, and it's a sort of planet that you can detect with the previous generation of spectrometers. So if we can go on to the next slide. So more recently, we've had a big breakthrough. We were able to combine HARPS data with another spectacular spectrometer called UVES, 8.4 meter telescope in the northern Atacama Desert, and this discovery actually made the cover of Nature. And this is a potentially habitable planet around Proxima Cen, which is the nearest star in the sky. So nobody will ever find an extrasolar planet that's closer to the solar system. And in the next slide, this discovery was only announced in August, and here you see the actual data, and you see the sets. There is set of square boxes, and that is from HARPS data that was taken between 2004 and 2014, and this is archival data that Minglada, and Guillaume and I had written a software package to reanalyze HARPS data called HARPS Terra, and with this new package we were actually able to. So Guillaume harvested all this data, and with these and the original data he harvested, that's the squares, and that showed hints of a planet in a days, and it was very exciting, but it wasn't good enough to publish. But with that data, Guillaume was able to get a high with the AAT, and that's the circular data. And that's also taken with HARPS. And that data was taken every single night at the end of the night from mid-January through the end of March of this year. And as you can see, that now fits on this 11.2-day orbit very nicely. The amplitude's about 1.5 meters a second. So it's a very, very teeny effect. All Guillaume had was data from HARPS, the HARPS archive data and the HARPS PRD, that stands for pale red dot, the name of this project. But it's all HARPS data, one telescope, one spectrometer, and one data analysis package. And Guillaume was very worried that there might be a systematic error somewhere. So it turned out that there's a spectacular spectrometer called UVES, which is on the 8.4 meter VLT2 telescope, and a group in Europe had been observing M dwarfs and Proxima Cen from 2000 to 2007 over an 8-year period, and in 2010 they had a scatter about 3 meters a second, and they couldn't see anything. Their errors were about 3 meters a second, and you're looking for a signal that's about 1.5 meters a second, and they didn't see anything. So Guillaume asked me to reanalyze the data because it was taken with an iodine absorption cell, in fact, a cell that I built. And I spent about 6 weeks earlier this year mostly doing bookkeeping and reanalyzing it, and that's the triangular data. It actually shows data with slightly less scatter. It has the exact same period, and it's in phase. In other words, when the UVES data is high, the HARPS data is high. And when the UVES data is low, the HARPS data is low. And now you have independent confirmation from 2 different telescopes, 2 different spectrometers, and 2 entirely different techniques. And that was what made this rise to the level that not only could we publish it, but that Nature decided to make it the cover story in late August. So if we can go on to the next slide. This is an example. This is the UVES data. So it turned out over that 8 years, they had one stretch of 16 nights where they observed it almost every single night. Again, high cadence. The red dots are what came out of the original UVES group, and you can see the error bars are relatively large. And the blue data is what came out of my reanalysis, and you can see the error bars are dramatically shrunk. And that, furthermore, the peak-to-peak velocities in the red data go up and down by about something like about 2 meters a second, and in the blue data, the reanalysis, they only go up and down by about 10 meters a second, and from this observation. So you can see it's not just the telescope, it's not just the spectrometer. An enormous amount of work has to go into the software analysis to extract the signal. So we can go on to the next slide. So here I sit in Australia talking to you in California, and I am essentially an astronomer. My wife says I don't live anywhere, I only visit. The green asterisk in Washington, D.C., that's where I pay mortgage, that's where I nominally live, but in fact I'm on the road half the year, and those red dots are Lick Observatory in California, Mauna Kea in Hawaii, Australian Telescope in Australia, and the Las Campanas Observatory in Chile. And usually I'm doing a big pattern like that, and it turns out if that's your pattern, living in DC is about the worst possible if you lived in Hawaii. But so far I haven't been able to convince my director to move us to Hawaii. So we can go on to the next slide. So, main goal right now is to find potentially habitable planets around nearby stars. But, when we find these planets like Proxima b, people quite justifiably say, but how do you know there's life there? And the truth is, we don't. We have no idea if there's life there. All we know is it's the right distance from the star to potentially have water. That's all we know. The huge new breakthrough in this field is going to be direct imaging. Pull out the light from the star, the original dream of people 400 years ago. And so here is one dream of how you do this. You have giant space-based telescopes acting as an interferometer to cancel out the light from the star to see the planet. And it's hoped that maybe by the 2030s, NASA or the European Space Agency, or maybe even the Chinese, will be able to launch such things. It's actually now becoming a race, because with giant ground-based telescopes, the Giant Magellan Telescope, the 30-meter telescope, and the European extremely large telescope, which are 25 to 40-meter telescopes, and advanced adaptive optics, you might be able to do this from the ground before you can do it from space. But again, it'll be the 2030s before this can be done. So if we go on to the next slide, we see an example of what one of these space-based interferometers will do. By combining the light from multiple telescopes, you can combine the light out of phase, so the light from the star cancels itself, and you can see the planet will now peak up, and there's a little arrow pointing to a potential planet. And frankly, assuming we all live into the 2030s and that all goes apace and that these things are detected, this is what we're going to see. The planet will be a single pixel. It won't be exciting. You won't see the aliens waving up at us from the espresso bars on the sides of the beaches. But the single pixel will be extremely exciting, because once you can separate the light from the planet from the light of the star, you can feed it into a spectrometer, and then you can begin looking for the composition of the atmosphere of the planet. And if you saw evidence for water vapor and oxygen or any gas that was far out of thermodynamic equilibrium, that would be one of the greatest discoveries in history. You wouldn't have proved there's life on that planet, but you would have flipped the question. Instead of saying prove there's life there, you would then be able to say prove there isn't life there, and it'll be an extraordinarily exciting new talk in the field of extrasolar planets. So if we can go on to the next slide. So finding life around really cool, and life is probably very common in the universe, but probably most life is single-cell creatures. On the Earth, the vast majority of life is single-cell creatures, and over the history of the Earth, for most of the history of life on Earth, life has only been single-cell creatures. What we'd really like to do is have something intelligent, something we can communicate with. And so, of course, this sparked Frank Drake inventing the SETI project going back in 1960, and Frank came up with one of the most well-known equations in the history of science, probably the second best known equation from the last century, called the Drake equation, where he tried to estimate the number of communicating civilizations in our own galaxy. So if you hit the next slide, you'll see the components of the Drake equation. And you can just read through that. You just basically multiply each of those things by each other, and you come up with a number of known of communicating civilizations. And the first one is the rate of formation of suitable stars, which people knew back in 1960. And then the fraction of those stars that have planets, the number of planets per planetary system, the fraction of planets where life actually develops, blah, blah, blah. So the thing is that until 1995, there were no known extrasolar planets. And so the only thing that was known was the rate of star formation. And what's gone on over the last 20 years is really remarkable, because now we know that virtually every star has a planet. So the next factor on that is basically 100%. Then we know the number of Earths per planetary system. We can now, between the Kepler mission and the ground-based Doppler velocity surveys, state that it appears that about 30% of stars have Earth-like planets that might potentially have water. So we now know the next two parameters. So after 50 years of knowing almost nothing, we've made this huge leap, and what these giant direct imaging devices in the 2030s will do is allow us to begin to answer the next question, the fraction where life actually develops. So we're making just really extraordinary progress over just a single human lifetime, where we had been stuck for 400 years. So, as the Chinese say, may you live in interesting times. So the Drake equation only applies to the Milky Way, to our own galaxy. If there's, so if we go on to the next slide, and we get a big picture of, the universe is composed of hundreds of billions of galaxies. And the truth is, if there were alien intelligences in any of these other galaxies, we'll never, ever, ever know. They're simply too far away for us. The nearest big galaxy to the Earth is Andromeda, which from there in Big Bear you can see with your naked eye, and it's about 2 million light years away. So the light that you see, you go out on a dark night and you can see it with your naked eye, the light that's hitting your eye has been traveling for 2 million years. The entire Homo sapiens, our species, is only about 200,000 light years old. So the light from that galaxy is 10 times all of our. So, the original word for galaxy was island universes, and they really are, because there's no way to traverse that distance. There's no way to communicate between them. It might be the case that every other galaxy has one intelligent civilization at any given time, and nobody will ever know of each other. We're just isolated and stuck. On the other hand, if our own galaxy has multiple intelligent communicating civilizations, there's some chance that we'll actually hear from somebody someday. So that's basically my talk, and I'll be happily taking any questions.